So what is asymptotic bounds? When we talk about bounds is that we're thinking of a boundary for the algorithm that, well, frankly, in most cases, that, hey, it's not going to get any worse than this. We're engineers, right? So what happens is that, again, we're looking at this line f of n. That's the real life line that we know that's going to basically follow that path as we add more and more data. But this f of n may be kind of tricky in the equation, stuff like that. So what we use is that theoretical line that's just above it, and there's actually another one that's going to be below it, and I'll talk about that here in a little bit. But what we want is we want a line that's going to predict pretty closely to f of n what that's going to be. And this is our way of saying, look, it's not going to run any worse than this. Now the the g of n can be right on it, so it's actually equal to or greater than f of n. Now you have to shouldn't say guess, but you should be able to predict your g of n pretty closely to f of n. Here's an example. Let's pretend n squared. Everybody knows n squared, and if you did a graph, it actually looked like this. But would you want to tell your boss that your application runs an n to the 12th power? Probably not. You would want to be as close as you could to saying, okay, look, it's going to run n squared. We've predicted it, f of n will prove that, but just in general, it's not going to run any worse than n squared, and that'll work out. Again, you're trying to do a prediction, and with the line, that simplistic line, which is going to be that g of n, of how close it's going to be is their tightly bound line to your literal f of n from there on out. There's three types of bounds which I'm going to go over, big O, big omega, and big theta, and I'll go over each one of them, but they're all related to the growth of our one function of f of n and how eventually it's going to go, well, up, but how? That's what we'll check out with the other bounds.